Using computer simulations to enhance teaching and learning. Have you been able to have your students vary the force of gravity and determine the effects of an object's motion? Explore the nuclear fission at the molecular level and discover whether the daughter atoms are always the same? Move tectonic plates while investigating the differences between divergent and convergent boundaries. Computer simulations make this type of interactive, authentic, meaningful learning opportunities possible. Learning can observe, explore, recreate, and receive immediate feedback about real objects, phenomena, and processes that would otherwise be too complex, time-consuming, and dangerous. Broadly defined, computer simulations are computer-generated dynamic models that presents theoretical or simplified models of real-world components, phenomena, or processes. They can include animations, visualizations, and interactive laboratory experiences. In a simulated environment, time changes can be sped up or slowed down. Abstract concepts can be made concrete and tacit behaviors visible. Teachers can focus students' attention on learning objectives when real-world environments are simplified, causality of events are clearly explained, and unnecessary cognitive tasks are reduced through a simulation. Technological advances have increasingly brought instructional digital technologies into the science classroom. Teachers may have greater access to the internet-connected classroom computers, wireless laptop cards, computer projectors, and interactive whiteboard than ever before. As you consider how these resources can be used to enhance science teaching and learning, you may find yourself turning often to computer simulations, especially since they are tools frequently used by scientists in their daily work. What does research say about simulations? Simulations have been around practically since the advent of computers, and researchers have been looking at classrooms' uses of simulations over 20 years. Researchers studying the use of simulations in the classrooms have reported positive findings overall. The literature indicates that the simulations can be effective in developing content knowledge and process skills, as well as promoting more complicated goals such as inquiry and conceptual change. Gains in student understanding and achievement have been reported in general science, process skills, and across specific subjects. Areas including physics, chemistry, biology, and earth and space science. This is according to Cooley. Although conventional instructional materials such as textbooks presents two-dimensional representation, simulations can offer three-dimensional manipulatives that bring the subject matter to life. Visualization results in the development of mental constructs that allow one to think about, describe, and explain objects, phenomena, and processes in a more true-to-life form. These are just the habits of mind scientists rely upon their daily work. For example, comparing simulated and hands-on dissection labs. According to Akpan and Ander, they concluded that the flexibility of these kinds of environments makes learning right and wrong answer less important than learning to solve problems to make decisions. Simulations promote learning about what-ifs and possibilities, not about certainties. Studies assessing the impact of simulations on process skills development, such as identifying variables, measuring, graphing, interpreting data, and designing experiments, have shown computer simulations to be equally as more valuable than traditional methods. For example, a study according by Geban, Askar, and Oskan investigated the effects of a computer-simulated experiment on chemistry achievement and process skills. The researchers found greater student achievement with simulated labs than with hands-on labs. And a study by means found out that students were successful in designing, implementing, and analyzing results of three ecological problems. Nothing improvement even as the inquiry task became increasingly complex. Students also began employing more formal analytic strategies rather than relying on trial and error. Trundle and Bird describes students' conceptual understanding about lunar concepts before and after instructions with planetarium simulations. Results indicated that students learned more about moon shapes and sequences, as well as causes of moon phases, by using computer simulations than by making actual nightly observation and studying nature alone. The ability to make many more observations